So I wrote down here, this is not in your notes, this is just a question for us to think about. Hey, what's more comfortable to drink a hot beverage out of? A metal cup or a styrofoam cup? Metal cup. Metal cup is more comfortable to drink hot coffee out of? Have any of you tried drinking hot coffee out of a metal cup? You won't enjoy it. Your hand's going to get burned. Okay? Oh, hang on here. Who we got? So what's more comfortable? Maybe you guys don't drink coffee, but I'm telling you, if you put a hot beverage into a metal cup, or even if you pour a boiling water into a glass and you try holding the glass, you're going to get burned. But you can pour that same boiling water into a styrofoam cup and you're going to be fine. So styrofoam, that's not in your notes. Why? Well, it turns out styrofoam is what we call an insulator. Metal is what we call a conductor. And now we can do some notes. So in your notes, it has the blank. Insulators prevent the flow of electrons or heat. Insulators prevent the flow of electrons or heat. You want some examples? Glass is a good insulator. Ceramics. Plastic is a pretty good insulator. So what does that mean? It means a balloon is a very good insulator. It means that if you add electrons or remove electrons, if you add charge, either positive or negative, to one part of an insulator, they are not replaced. And what that means is that a static charge builds up. I think this time Leah has a good sweater. Did you get on all yet? Did Static get on yet or not? Okay, let's see. It was close. I heard it crackle. Once instead. Close. I need to put more charge on there if I did that. Okay? A balloon is an insulator. So what's happening is, first of all, there's a bunch of charges building up on it. They want to repel each other. So Nicole, they're going to gather around the outside of the balloon, spread out as much as they can, but they can't go anywhere. Why? It's an insulator. The insulator does not transfer charge very well. Charge can build up. Why can't you rub a piece of metal on wool and stick it to a wall? And it's not because of the weight. You could try it with tin foil if you wanted to. So here's a picture of an insulator, and the charge is building up. It can't move anywhere. Conductors, next line. Conductors allow the flow of electrons or heat. Hey, you want some examples? Metals. And what does that mean? That means that electrons removed from or added to a conductor, they're replaced. So a static charge does not build up. Or, sorry, don't need to underline the word does not. You can underline the word static. Static means unchanging. The problem is if you add electrons to metal, it's just going to go shooting through the metal and try and find a way out the other end. It's why, Mitra, we make wires out of metal. We would not make wires out of rubber or plastic because we could not send the electricity through the wires very easily at all. Metal, sure, it'll go out the other end very quick. So we have conductors, you don't need to know that word. We have insulators, you don't need to know that word, you need to know the difference. Insulators do not transmit charge easily. Conductors do transmit charge easily. So, just a question for you. Which of these do you think would allow the buildup of a larger static charge? A copper rod or a plastic drinking straw? What do you think? Sure, Amelia, what do you think? Copper rod? No. It's a conductor. It won't build up any static charge. As soon as you add any electrons, extra electrons to the copper rod, it's going to go shooting through, and whatever it touches, it's going to distribute it to that. Okay? So key idea, insulators let you build up static charge. I know it's not in your notes, but I'm going to ask you a question like that, certainly. Okay, does that make sense? Yeah, yeah, yeah? You guys are tired this morning, I know. I'll start shocking you in a bit. A drinking straw. It's an insulator. You can add a whole bunch of extra charge. They'll gather around the outside, but they won't go anywhere. It'll hold charge. I showed you this one yesterday. Don't worry, it's just electrostatic discharge. You saw the guy getting shocked quite a bit. So, this explains how you can get a shock on a cold, dry day after walking across a carpet and touching a metal door. I get a shock almost every morning when I take off my big winter coat. My big winter coat is not a very, very good conductor at all. It's an insulator. It picks up a lot of charge when I'm driving, when I'm walking, because it rubs on my body. When I hang it, I know I'm always charged. I always hang it in the little office there, and every time I touch the doorknob, I get a shock. I get a shock. What's happening when I get a shock? Well, let me show you good old John Travoltage. John Travoltage, absolutely. So when you walk across a carpet, your feet are rubbing against the carpet slightly. Even if you're trying to pick your feet up as even as possible, Omid, you're still rubbing against the carpet. And what you're doing when you do that is you're rubbing some electrons off. Okay? Now, initially, the electrons are going to gather on the outside of your body. Nicole, that's what you were feeling last class when I can feel the static on me. They're gathering on the outside. As a matter of fact, the furthest they can get away from you when it's on your skin is on the hairs on your skin. That's why your skin feels weird. What's really happening is you're feeling the hairs standing straight up, repelling each other as much as they can. That's why when you're feeling staticky, that's what you're feeling. Eventually, if you get enough charges, they're repelling each other, they're repelling each other. Now here's the problem. Air is not very conductive. So right now, John Travoltage has picked up a bunch of charge. Air is not conductive. The electricity does not have enough energy to jump this gap. But air is somewhat conductive. Small gaps, it'll jump. Okay? If we go to our notes then, here's what we said. As you walk across the carpet, your feet rub electrons off the carpet, and they flow onto you. And I think I said to you last day, and I'll say it again, heck, during this whole unit, in those plastic chairs you're sitting in, you rub your back and forth, especially if you're wearing the right kind of shirt, you can build a lot of charge up on yourself, and you can give somebody a pretty nasty shock. Then the electrons, well, they're like charges, so our word is they're going to repel each other. So they're going to gather on your skin, on the outside of your skin, which is actually a good thing because your internal organs are much more sensitive to shocks. If they gathered on your internal organs, it could actually do physical damage. When you touch the metal door, metal is a conductor, and so Amelia, the conductor, is happy to accept charge and pass them along. That's the copper rod straw example from before as well. The electrons leap onto the door, and you get an ouch. I think I included a little chart in your notes. It turns out for conductors, they have different abilities to absorb electrons. Oh, I have to bring out the electric shock ball. Of course I do. So here's a little chart I gave you. You can actually predict if you're rubbing two objects together, which one will be positive and which one will be negative. Because the objects going this way have a tendency to lose electrons. If you lose electrons, will you become positive or negative? Think about it. Positive. These ones have a tendency to gain electrons. If you gain electrons, will you become positive or negative? Negative. So, suppose you were doing an experiment. Suppose you were rubbing wool, and you can write this. You have a little bit of room beneath your chart. Write the word wool. Write the word, balloon. So if I rub those two together, which one would end up becoming positive, losing electrons? Which one would end up becoming negative, gaining electrons? Look at where they are on the chart. Look at how they relate to each other and see if you can figure it out. Which one is more willing to gain electrons, a balloon or wool? Balloon. So this would become negative, this would become positive. Okay? What if I rubbed glass and silk together? If I was rubbing a piece of glass with silk, would I be adding electrons to the glass or would I be rubbing off electrons? So which one's going to be positive, which one's going to be negative? Glass had a tendency to lose electrons. When you lose electrons, what do you become? Do you see why Ben Franklin named, they are backwards, because you say, you're losing, it's a minus, it's a plus. Yeah, minus, minuses. That's going to become positive, that's going to become negative. What if I rub the silk onto vinyl? What if I rub the silk onto vinyl? See how we can figure it out from the chart? Would vinyl become, compared to silk, will vinyl be gaining electrons, negative, or losing electrons, positive? Find them on the chart. Vinyl's going to actually, yeah, this is kind of a strange one. So if I'm rubbing silk and glass, I'm rubbing electrons off the glass. If I'm rubbing silk and vinyl, I'm rubbing electrons onto the vinyl. Sort of. Okay? So as part of your homework, I'm going to be giving you this chart as an assignment and giving you several things to rub together, and you're going to have to think to yourself, oh, positive or negative, which one's going to become which? And this allows us to make predictions later on when we're doing labs and stuff as well. Turn the page. Here's the problem. One electron, although it does have negative charge, that negative charge, Nicole, is so small, we need to measure charge in a different way. In fact, you know what? If you go to a grocery store, you don't buy one egg at a time. You buy them in, well, a group of them. In fact, what do we call that group of eggs usually? Dozen. Why? Because one egg's so small. Okay? Is there a name for an even larger group of eggs? Yeah, a dozen has a name as well. Begins with the letter G. Does anybody know it? Okay, it's called a gross. 144. 12 12s is a gross. Those are the big square egg packs that you can buy as well, the 12 by 12. Well, we sort of do the same thing, Riley, with charge, although we don't call it a dozen. One electron is so small, like one egg, except it's really, 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 really small. Measuring charge. First of all, a neutral object has an equal number of electrons and protons. So when I say something's neutral, I'm not saying it has no electrons and protons. I'm saying, hey, if it's got 1,000,000,001 electrons, it's got 1,000,000,001 protons. If it gains or loses electrons, we need a way to tell how many have moved. So an electron is so small, well, we count them in groups. So what's the unit of charge that we have? We measure time in seconds. We measure mass in kilograms. We measure distance in meters. What do we measure charge in? Here it is. We measure charge in coulombs. Now, from now on, if you want to, you never need to write the word coulombs again. The abbreviation, the same way that meters abbreviation is lowercase m, same way that kilograms abbreviation is kg. Coulombs, capital C. It has its own abbreviation in the metric system. Capital C. Named after a scientist whose last name was Coulomb did a lot of work with electricity. In fact, in Physics 12, you learned something called Coulombs Law. Turns out, 1 Coulomb contains, and you can write this, 6.25 times 10 to the 18th electrons. You don't need to know this. All you need to know is that an electron has a really small, you know what? It's 625 and 15 more zeros. Million, billion, trillion, quadrillion, 6 quintillion, 250 quadrillion electrons in 1 Coulomb of charge. Now, a lightning bolt typically contains 15 coulombs. 1 Coulomb would probably kill you. If you absorbed it all at once. If you absorbed it over an extended period of time, you'd be okay. But if you absorbed 1 Coulomb all at once, almost certainly, Kiana, it would send you to the hospital. Probably do permanent damage. We'll talk about how that works later on. So 1 electron has a charge of, oh, by the way, 1 lightning bolt typically has a charge of 15 coulombs. You don't need to memorize that, but it's lightning, it's cool. Anyways. 1 electron typically has a charge of negative, because electron's negative. It's 1.6 times 10 to the negative 19. Now, this is something called scientific notation, which is a short way to write long decimals. 1 electron has a charge of 0.00000000000000000000000000016 coulombs. Do you see what I meant, Amelia, when I said electrons are a really small charge? We're not going to count electrons. Proton has the same charge as an electron, but positive. You want the charge on a proton? Positive 1.6 times 10 to the negative 19, or positive point. Oh, by the way, I guess technically there should be a negative in front of there since I'm talking about an electron. Let's look at some cool applications. Oh, one of my favorites. The Van de Graaff generator. Put your pencils down. So one really fun one is the Van de Graaff generator. Yeah, named after a Dutch scientist whose last name was Van de Graaff. He invented this little toy. It's a fun toy because it can generate a big voltage fairly safely. It can generate lots of charge. You know what? Saran wrap actually works the same way. Think about it. When you pull the saran wrap off the roll, that's the same as rubbing a balloon. You're literally pulling some electrons off. That's why the saran wrap is so clingy when you put it onto a neutral bowl. So another application, saran wrap. You can write that down. Cool applications. So, Van de Graaff generator. Saran wrap, it clings because of static charge. Another application, reducing air pollution. So if you have something, that an electric device that claims to remove dust from the air, all it does is it attracts charged dust particles. Especially if the dust particles are neutral, they'll be attracted whether the device is giving a negative or a positive charge. So reducing air pollution, small charged particles of dust are attracted to collectors. By the way, this is why dust sticks to computer screens, because computer screens are slightly charged and the dust particles are neutral, and neutral objects are attracted to any charge. Painting cars. Really? Yeah. The paint particles in factories are given a charge, and then they're sprayed to the metal car, and they stick. In fact, very similar, where's Nicole back there? Very similar to the balloon sticking on a wall. In factories, they've just taken that to an industrial scale. Quite clever. Dangers. Besides the obvious shocks can be owie, turn the page, what are some dangers of static electricity? Well, we actually have to take this into account in the quote-unquote real world, because static charge on the industrial scale can build up pretty intensely. So the biggest danger is the generation of sparks around fuel. Yep. Not just gasoline, all kinds of fuel. Okay. read the news once or twice a year in Canada, somewhere a barn explodes because the dust particles of grain are actually flammable and there's a spark in the barn somewhere, boom. Airplanes and trucks must be grounded. And I've noticed I didn't give you a definition of grounded, but we just wrote down the word. So where it says dangers of a static electricity, you got some room. Grounded, this means attached to the earth. Why? Because the earth can accept an unlimited number of charges because it's so big. Okay, technically not an unlimited, but almost an infinite number of charges. Grounding, I did add a definition this year. I forgot to add it last year, Lindsay. Grounding is allowing excess electrons to flow into the ground, which has an unlimited ability to absorb electrons or give up electrons. Whether you're charged positively or negatively, the Earth can either absorb or give up electrons, no problem. Put your pencils down. It says for lesser crimes, there was the static electric chair. Rub a balloon and get a shock. Our bodies can handle shocks fairly well. In fact, in a few lessons from now, I'll talk about what kind of shocks will kill you, what kind of shocks will injure you, and what kind of shocks will just wake you up. And that's why, Youngjun, I gave you shocks today. I knew it was perfectly safe. I knew you'd get a bit of a owie, but nothing beyond that. Little Garfield comic. Garfield's giving shocks. He says, I love static electricity. Cats often can pick up some pretty good static electricity because they're furry and they often do rub on carpet on a dry day. And then he touches his food, it explodes, and he says, I hate static electricity. Assignment. For now, section 7.1, you can work on that, but I also got another cool video to show you. So this, I'm going to say, is homework, but you'll get time tomorrow as well, but you want to get a head start. Let me walk you through what I gave you right now. So first of all, some vocabulary, words to know. See if you can fill in the blanks as you go through it. Then this is that chart that I gave you in the notes as well. So it's going to be asking you to figure out if you rub these together, which one will be positive, which one will be negative. Again, if it's to the right, it'll be the negative one. If it's to the left, it'll be the positive one. Then on the third page, you're being asked to define conductor and insulator. Those are very, very, very important terms. And then the only thing that I didn't like, this diagram here wasn't very clear, and neither was this diagram. So I said, I typed in, this is an aluminum stair, and this is a brush made of tinsel. Those are like little metal brushes. So you can ask whether it's a conductor or an insulator. It's usually pretty obvious. You need to know the difference, and then fill that in. You got 13 minutes. If you get it done in class, great. You'll also get some time tomorrow. Tomorrow we'll also watch a Bill Nye video.